Right now, we're going to take a look at optimization, which is finding extreme values, which includes max and min. So this is an application of derivatives, and the basic idea should be familiar from single variable calculus. Now, of course, we're going to apply it to multivariable functions. Now we're going to look at three different types of problems where we're asked to find the extrema. First, which we're going to focus on in this video, is to find local extrema. After this, we're also going to look at global extrema on a boundary, which is also called a constraint. And then after that, we're going to put all the techniques together to find global extrema on a region. Right now, we'll take a look at local extrema, so let's get started. Finding local extreme values. So just to recall back from single variable calculus, function of one variable, to find the local max and min, there's the need to identify critical points, which we have when the derivative of the function is 0 or undefined. So what does it look like when we have a function of two variables? So how can we find all the local extreme points? So once again, we require that the derivative must be 0. Now, as we've previously seen, there's more than just one derivative. So in order for all derivatives to be 0, that simply means that all the partial derivatives must be 0. And another way to interpret this geometrically is to say that the tangent plane must be horizontal. So looking at this graph, we can see that we have things like maxima and minima, things like that. And in every case, at every peak, you can imagine what the tangent plane would look like, the fact that it would be flat. Now, just like in single variable calculus, once again, there might be some critical points which are neither max nor min. Also, once we have a critical point, we're going to want to determine if it is a max or a min. And now in 3 dimensions, there are new ways for things to be either a max or a min or neither. So how do we once we have our critical points, how do we classify them? So let's take a look. Here's an example. So in this graph, at the point in the center, 0, 0, 0, we can see that the df dx equals 0 and df dy equals 0. We can also tell the point is neither a local max nor a local min. This kind of point is called a saddle point, so named because of the general shape of the graph. So the way that we can classify a critical point, is using the first we find critical points using the first derivative test, which is just df dx equals 0 and df dy equals 0. Could also be undefined. Next, to classify critical points as either a local max, local min, or neither, we use the second derivative test. This one's a little more complicated than we saw in single variable calculus. So we calculate something called the Hessian, which is defined in the following way. Hessian H equals fxx times fyy minus fxy. Now, really, it's fxy times fyx, but as we know from Clairaut's theorem, typically those are the same thing. So we can just say fxy squared. So there's the Hessian. Now, if the Hessian at a critical point is a saddle point, if the Hessian is less than 0, then the point is a saddle point. If the Hessian at a critical point is greater than 0, then we know it's a local extreme point. We're not done. We need to determine if it's a max or a min. Now we kind of use the second derivative test from single variable calculus. We calculate fxx at that point, and if it's positive, then we know the graph is concave up and the point is a local min. And similarly, if xxx, second derivative, is less than 0, then the graph is concave down, so the point is a local max. So I wrote this using the second derivative with respect to x. You could also do this second derivative with respect to y. And finally, if the Hessian at a critical point is 0, then we say there's no conclusion. There are other fancy tests to tell at that point. We will not worry about that or go that far. We'll simply stop there. Okay. So to calculate the Hessian, if you're familiar with linear algebra, here's a linear algebra tip. The Hessian can be written as this determinant, sort of the determinant of this matrix of all second partial derivatives. Okay, so let's use this on a problem. Let's take a look. So let's find the critical points of this function, f equals x to the fourth plus y to the fourth minus 4xy plus 1. And then we'll classify each one as a max, min, or neither being a saddle. All right, so let's take a look. First, we're going to find local critical points. So we need fx to be 0, and fx is 4x cubed minus 4y equals 0. And solving that out, solving for y, you'll get y equals x cubed. And then we also have fy. And that is 4y cubed minus 4x, and that must be 0. And now we can most easily solve for x, and that gives us x equals y cubed. So now we combine these expressions, and we get x equals y cubed, y equals x cubed. Therefore, we get, putting it together, x equals x cubed cubed. Or in other words, x equals x to the 9th. Okay. Now, there's two ways to solve this polynomial equation. You could actually go through the process of factoring. It's a little tricky, but you can do it. Alternately, we can go ahead and try to apply common sense. What number could possibly be raised to the 9th power and still be itself? And if you think about that, there's really only a couple of possibilities. One possibility, pretty clearly, is that x would be 0. Another possibility is that x is 1. And then if you think about it cleverly, you see that another possibility is that x is -1. And further, it's clear that no other number could possibly make this true. So 0, 1, and -1. And then when x is 0, substituting, we get that y equals 0. And when x is 1, substituting, we get y is 1. And then when x is -1, substituting, we get y is -1. So that gives us our critical points. So our critical points are 0, 0, 1, 1, and -1, -1. So we have 3 critical points, and we will need to check them. We're going to need to test them using the second derivative test. So for that, we need to calculate the Hessian. So for that, we're going to need all of the second partials. So fxx is 12x squared. Fyy is 12y squared. Fxy, which is the same as fyx, that just equals 4. And now we know that the Hessian equals, put it all together using the formula for the Hessian, 12x squared times 12y squared minus 4 times 4, or you could just write that as 4 squared. So doing a little bit of simplifying, you get 144 x squared y squared minus 16. So there's the expression for the Hessian. And now we can test our critical points in order to classify them. So the Hessian of 0, 0, plug it in, you just get negative 16. Since the Hessian is negative, it's a saddle point. Next, we calculate the Hessian at 1, 1. So plugging that in, 144 minus 16, you just get 128. So therefore, it's a local extrema, and we need to go further. Second derivative, fxx at 1, 1, plug it into 12x squared, and that just gives 12. Therefore, the graph is concave up, and you get a local min. Finally, the Hessian at negative 1, negative 1, plugging it in, you get 128. So it is a local extrema. Then we have to check to see which kind of local extrema. So fxx at negative 1, negative 1, plugging that in, and you get 12. And once again, concave up, and it's a local min. So we found three critical points, and we classified each one. 0, 0 was a saddle, 1, 1 is a local min, and negative 1 is also a local min. Okay, so just for fun, I've also got here the graph of the function, and we can take a look at that. And taking a look at the graph, we can see our critical points and how our classification matches up with the graph. The two local mins are pretty straightforward. You can see down at the bottom right there and down at the bottom right there, we've got two local mins. And then you can imagine sort of in that kind of upwardish sort of area between them, we're going to have a saddle point where the graph is kind of going like this between the 2 points, but then going like this in the other direction. So over right around in here somewhere, that's the middle of the graph, that's 0, 0, and that's where you get your saddle point. Okay. So that is how we can use the first derivative test and the second derivative test involving the Hessian in order to first, for a function, find our critical points and then classify them as either a max, a min, or a saddle.